Welcome everyone to part 4 of Math and Measurements. Few objectives for this one: distinguish between precision and accuracy, convert between the Celsius, Fahrenheit, and Kelvin temperature scales, and solve problems involving density. So let's go ahead and jump right into it here. Now let's start with density. Okay, density, if you recall, is a measure of how much mass is contained in a certain amount of space. Remember, it's not how much something weighs. So you think dense, you think of something heavy, rocks, right? A boulder is dense. Not necessarily that means. The reason they're so dense is because they have so much mass packed into a small space there, right? And to calculate density, we have the formula density equals mass over volume. That's what M and V stand for. M is mass, V is volume. In other words, density equals love. Density equals love. It's going to help you remember the formula. How do you remember that? You're going to draw a heart and then draw a little arrow going through it. You have mass over volume. So here's an example. The density of alcohol is 0.8 grams per milliliter. What is the mass of 50 milliliters of alcohol? So what are we looking for? We're looking for density. We're given density. Okay, there it is, density of alcohol. So here is density. What is the mass? So we're looking for mass. That's our question mark. What is the mass of 50 milliliters of alcohol? So here's our question mark. We're given 50 milliliters for our alcohol, and density is given to be 0.8 grams per milliliter. Okay, don't forget your units there. So if you plug everything in, 0.8 grams per milliliter, and that's equal to M. We'll just keep it as M. If you want to switch it to X, that's fine. Milliliters. Okay, so how do we get mass by itself? Well, if you're good at algebra, let's see, we can multiply both sides by 50 milliliters. Multiply this side by 50 milliliters so that these two cancel out. And now we're left with 50 milliliters times 0.8 grams per milliliter. Notice how I'm writing it right, kind of visual. And that's equal to mass. So what's going to happen with milliliters in this numerator and milliliters in this denominator? Because this is technically 50 milliliters over 1. So milliliters here is in the numerator, here it's in the denominator. They're going to cancel each other out, and I'm going to be left with just grams. So 0.8 times 50. One very important thing you need to know about density. In regular chemistry, even biology, even physical science if you took it, when you dealt with density, it was very similar to this type of problem where you're given two values and you're asked to solve for a third. In AP Chem, you're going to be using density as a conversion factor. So what does that mean? Okay, what does that mean? That means that you're going to be using density, which has units of grams per milliliter, as a conversion factor to convert between mass and volume, right? So you can write it, not equal to, or either way. You can write it as grams per milliliter, or if you need it to convert, you can write it as milliliters per gram, right? All you would do is flip the number. So if we had 0.8 grams per milliliter, when you wrote it this way, you would have 0.8 grams per milliliter, right? Because it's technically per milliliter. So now I can use this as a conversion factor either way to cancel out units. So there it is. This is the main idea here for density. Okay, we can use it to convert between mass and volume. Okay, that's super important. Make sure you understand that concept. So let's talk about temperature conversion. Three types of temperature scales: Fahrenheit, Celsius, and Kelvin. In the lab, we will always use Celsius. Okay, we'll never use Fahrenheit. Fahrenheit is what you see on TV mostly. Kelvin scale, when we work with gases, all of our calculations have to be done in Kelvin. All of our measurements, though, are going to be done with Celsius. And remember, the Kelvin scale is based on the concept of absolute zero, the point at which molecules stop their movement and contain no heat energy at all. Theoretically, can happen that we know of. So formulas, here you go. Memorize them. That's all I can say about them. Especially Celsius to Kelvin. Very important. So let's go through this example. Body temperature on the average human body is 98.6 degrees Fahrenheit. What is this in the Celsius scale and the Kelvin scale? So let's do the Celsius scale first. There it is. We're given our Fahrenheit. Let's plug it in, 98.6 minus 32. And the way that you have to do this is order of operations. Okay, top part first. You should still come out the same, but just in case, subtract the top part and then divide. And then you should come out with 37 degrees Celsius. And convert that to Kelvin. Plug in 37 degrees Celsius and add 273 to get 310 Kelvin. Remember, you have to find Celsius first before you can convert to Kelvin, because there is only one formula to convert to Kelvin, and that is from Celsius. Let's talk about precision versus accuracy. Often when doing labs, you need to repeat your measurements to verify your results. Accuracy, how close you are to the real answer, versus being precise is how close all your measurements are to each other. Let's do an example of observing this data table right here. So look at student 1 versus student 2. Student 1 has 3 trials, student 2 has 3 trials, and their averages are written down below as 26.3 and 26.5 respectively. Now, our real answer is 27. Okay, who was closer? Student 2 was closer. Okay, we can say he was more accurate. But if we take a look at the results, or I'm sorry, at the results of each trial, we have 21, 30, and 28. So there's a large gap here. Okay, 28 is close, but these two we can even say might even possibly be an outlier. Definitely 21 would be an outlier. Kind of just hanging out there, right? So we wouldn't say these are precise, but his average to his compared to the real answer is pretty accurate. Now, student 1 was pretty precise. He got 25, 28, and 26, which is pretty close to 27 there. So he was precise. But when you average those out, not too accurate there. So again, student 1 was more precise. Which student was more accurate? Student 2 was.